So today we're going to be talking about two different things. One is called a linear approximation, and one is called a differential. So another couple words for linear approximations are linearization or tangent line approximation. So these are two other ways that you can say linear approximation. So just a reminder that your tangent line approximates a value where you have an x value getting very, very close to some a value. So your slope of your tangent line, f prime of a, if you had a tangent at some value a, your slope of that tangent line is a limit as x approaches a for some other value x over here. So if I had a point on my tangent line, right, this x would be getting very, very close to a. And as I bring that x really close, I would get very close to having a slope of a tangent line at this point. Okay? Now, the problem is if we don't know the line yet, we can't draw it like that. What we would have to look at is if you had your x value on your curve, the slope between x and a, those 2 points, if I had a line going through these 2 points, this line, as I bring x closer and closer to a, this line would get closer and closer to overlapping the tangent line that's already drawn. So if I drew my x here, my line would look like that. And the closer x gets to a, the closer the slope between the 2 points x and a gets to being the slope of the tangent line. So let's just fix up this drawing a little bit here. So I have my point A, which is my point of tangency, and I have another point X on my curve. And the slope between those two points, we know from grade 10, would be f of x minus f of a, or a delta y value, change in y, over x minus a, which would be a change in x. And as x gets closer and closer to a, this gets very close to being the same as the slope of the tangent line. And the slope of the tangent line we know is f prime of a. So that gives us our little equation here. So your tangent line approximates f of x values for values of x close to a. This means the limit as x approaches a. So x is getting very close. So if I say that x is getting very close to a, and therefore my slope of my tangent, f prime of a, is approximately this delta y over delta x, or f of x minus f of a over x minus a. I can say I know that this is true if x is getting very close to a. Now I can rearrange this, and the reason I'm going to do that is to isolate my f of x. And so what we're looking at here is basically if you have an f of x you're trying to find, but maybe it's an obscure value, but you know a nice point nearby or an a value nearby that is nice and neat, we can use f of a and f prime of a to help us determine our f of x. So it's kind of like we're working backwards. Normally, we're trying to actually find the slope of the tangent. What we're saying is if we know the slope of the tangent line and we know the point of tangency, we can find f of x values nearby by using this approximation that is true. Okay, so I'm going to rearrange my formula here. I'm going to multiply both sides by x minus a, and that's going to give us f prime of a times x minus a is approximately equal to f of x minus f of a. And then if I move f of a over to the left, I get f prime of a times x minus a plus f of a is approximately equal to f of x. This is what our linear approximation formula is. So if we are asked to find an f of x value where given the x that we have and given the function we have, we can't do this easily. We can use the point of tangency and the slope of the tangent line to help us come up with a value, an approximation for f of x. So we're going to do a couple examples of what I mean by that. And again, we have calculators, so you would be able to calculate these things, but we're using calculus to show us how things are related here. Okay. So if I wanted to find, for example, these two values, I want to find 2.03 squared, and I want to find the square root of 49.6. Okay, so we're going to start with example 1a here. So if I've been given 2.03 squared, that means that my x is 2.03. And my f of x here would be x squared. So what I'm being asked to find is 2.03 squared, right? So my f of x would be x squared, and my x is 2.03. Now, if f of x is x squared, I know f prime of x is 2x. So I need to pick an a value that's really, really close to 2.03, but I can easily square that, and I can easily do 2 times that. So I would pick an a value of 2. 2 is very, very close to 2.03. So I'm going to say, let a equal 2. Then f of a would be 2 squared, or 4. F prime of a would be 2 times 2, which is also 4. And therefore, we can approximate f of 2.03, or f of. So f of 2.03 from our formula above is approximately f prime of a, or 4. I'll write it all out. F prime of a times x, which is 2.03, minus a, which was 2, plus f of a, which is 2, f of 2. So f prime of 2 is 4. 2.03 minus 2 is 0.03. F of 2 is also 4. So this gives me approximately 0.12 plus 4, which means f of 2.03 is approximately 4.12. So we can do that with no calculator. We could obviously check this answer on a calculator, but the point is that we're saying now, instead of finding f prime of a or x, and instead of finding a point of tangency, we're being told pick a point of tangency very close to the point you're actually concerned about. And if we know the slope of the line at that point of tangency, we can figure out information about that point that we are very close to. So there's a couple steps here. Step 1 is figure out what f of x is, which was right here. So what function are we actually dealing with? Okay, step 2, pick an a. It should be very close to your x. And it should be something you can do in your head. Okay, so this was what we did here. Step 3, we would need to find f of a and f prime of a. So that's what we did right here. Okay. And step 4 is use the linear approximation equation we were given. This guy in red. Use that linear approximation formula to find f of x. So that's what we did here. Okay, this whole, let's fix that up. This whole step here. Okay. So we're going to try this again with b. So step 1, figure out what f of x is. My f of x here looks like it's probably root x, right? Or x to the power of 1/2. Step 2, pick an a very close to our x value. So my x value is 49.6. So I could pick 50, but can I square root 50 easily in my head? No, I cannot. So I'm going to pick 49. Okay. I also need to find f of a and f prime of a. So actually, before I do this, let's find f prime of x. Just it'll make it easier when we get to doing f prime of a. So our f prime of x would be 1/2 x to the negative 1/2, or 1 over 2 root x. So now I'm going to say let a equal 49. That's something very close to our x that I can actually square root. So f of a is going to be root 49, or 7. F prime of a is going to be 1 over 2 root 49, or 1 over 14. And then I can use my linear approximation formula to get a value for 49.6 square rooted. So f of 49.6 will be approximately f prime of a, which is 1 over 14, times x minus a, which would be 49.6 minus 49, plus f of a, which is 7. So this gives us approximately 0.6 over 14 plus 7. Now this one you would need a calculator for to do your 0.6 over 14 bit and add that to 7. And so if I plug this portion I have here in my calculator, this bit here, into calculator, I get approximately 7.043. And so you have to plug square root of 49.6 into your calculator and see how close that is. Okay. That is linear approximations. The next bit for today is something called a differential. Okay. So the key part here, the drawings can get a little messy. So sometimes I would suggest drawing yourself multiple pictures. Okay. So delta x means an increment in x or a change in x. Okay. Delta y, we can view as f of x plus delta x minus f of x. And I'm going to show you y on my picture in a moment. This is change in y. So if I look at my curve I have here, if I have an x value, okay, let's call this x1, and I have another x2, this change would be delta x, right? And so the point on my curve, this would be f of x1 here, and this would be f of x2. Now, the other way I could write x2 is saying x1 plus delta x, which means the other way I can write f of x2 is actually f of x1 plus delta x. and that's where this comes from. So my change in y is always y2 minus y1. This is my y2. This is my y1. So if I do y2, I can write that as f of x1 plus delta x minus f. So this here would be my delta x on the bottom. This here would be my delta y. So I just want to show you where your dy and your dx are coming from. That comes from your slope of your tangent line. So you'll see we've got dy and dx up here. Okay. So delta y and delta x represent the change in y or the change in x on the actual curve. Dy and dx represent the change in y and the change in x on the tangent line. Okay, so I'm going to draw two pictures on the next page that show the difference between these two. Okay, so if I have my x1 here, my point of tangency, my f of x1 is the y coordinate of that point of tangency. This curve is your f of x. And this straight line is your tangent line to f of x at the point x1, f of x1. Okay. All right. So if I want to look at the tangent line, if I were to draw a second point, x2, that point on my tangent line would lie about here. And my f of x2 would go here. Okay. So this is on the tangent line. Okay. What that means is if I draw in my little triangle to find the slope of this tangent line, we use dy and dx to represent your slope of your tangent line, which makes my rise dy and my run dx. I can also write x2 as x1 plus delta x. Now, the problem we have is that we have this point on our tangent line. So I shouldn't have called this f of x2. I should have called this f prime of x2. Or I could have called it f prime of x1 plus delta x. And you'll notice that if I draw the same point, x2, and put that point on my original curve instead of my tangent line, purple points are not in the same spot. Blue point still is. The blue point is the point of tangency. Okay? So it touches both the curve and the tangent line. The purple point is some other point x2. If I put that point on the tangent line, we see that our y value is different than if I put that point on the curve. My x1 and x2 are still drawn in the same location. Okay, so this distance here is delta x. This distance here is also delta x. Okay, but now you'll see if I draw my change in y and change in x with respect to my original, delta x and dx are the same here, but my delta y and my dy are different. This is the point where it was on my tangent line. And you'll see that my dy, my change in y is bigger if I look at the actual curve here, right? So you can see dx and delta x are the same, but dy and delta y are different. So if I put my y coordinate on my y-axis, I get f of x2 or f of x1 plus delta x, whereas on tangent line point, the y coordinate f prime x2 or f prime x1 plus delta x. So the point of tangent C is a y value on both my original curve and my tangent line. So by definition, the tangent line must touch at a specific point, and that's what we have. So the blue point is the same on both graphs, but as soon as I draw a second point, if I put it on my tangent line, it's going to have a different y value than if I put it on my original function f. Okay. So from the previous page, you'll see that we know that f prime of x is equal to dy dx. We know that those are the same. And I can rearrange this and write this as dy equals f prime times dx. That's called differential form. Okay. dy and dx are called differentials. So we're going to do a question where we use these. Again, sometimes these can get a little messy, so it might be helpful to draw two different pictures. I'm going to try and draw it as clear as I can on one so you can see the difference in dy and delta y. Okay. But if you need to draw two pictures, that's fine. Okay. Now, there's some math that we're going to want to do to make this a little easier for us as well as we go. Okay. So first, let's draw ourselves a picture. Okay. We're trying to draw x squared. And if we read part B, it's telling us we're eventually going to want to find dy and delta y at x equals 1. So I want some information about x equals 1 on my picture. And I've been told that dx and delta x, remember those are the same on both the pictures we drew above, dx and delta x equals 1. So what that means is my scale along the x-axis is going to go up by 1s. So I'm going to have an x value of 1, an x value of 2, maybe I'll do an x value of 3, and we'll go -1, -2, -3. Okay, we'll go up by 1s here, so I'll go 2, 4, 6. So if I want to draw my curve in, okay, I know that I've got y equals x squared, so I've got a point at 0, 0. I've got a point at 1 and -1. I've got a point at 2 and 4. And my next point I can't draw because 3 and -3 would be off my grid that I've got going on here. Okay, so this is y equals x squared. So right away, we could draw at x equals 1. We know that delta x is 1. So from x equals 1, this point, over to 2, where is my corresponding y point? I can find delta y, purple here, right? My delta y would be this guy, and my delta x would be this guy. So if I take a look at the coordinates of the points, right? My point 1, my x1, y1 is equal to 1, 1. And my x2, y2 is equal to 2, 4. So we can see our change in y is 3, right? And you can do that algebraically using the points, but we can also see that in our picture here, right? Now, the other thing it's asking us for is dy. So dy, I'll do some green, dy is the change in y on our tangent line. So this is your change in y on f of x. Okay. dy is the change in y on our tangent line. So now what I would prefer to do, we know from the previous page, we know that dy is equal to f prime dx. And so we can do this purely algebraically. But if we wanted to do this graphically to show delta y, so dy was in purple, oh, whoops, dy, delta y was purple, sorry. Dy is going to be green. what I would choose to do is find the equation of my tangent line so that I can draw it here so that I can show dy. Okay. So I know that if f of x is x squared, f prime of x is 2x, and at x equals 1, f prime of 1 would be 2. So that's my slope of my tangent line. So if I'm starting at x equals 1, my slope is 2. So rise over run, 2 over 1. So I'm going to go up 2 over 1, up 2 over 1. If you want to go down 2 over 1, you can as well. Although my scale wasn't great, so it's not working out so nicely. And so my tangent line would look roughly like this. Okay. Now, as soon as we know our rise over run of our tangent line, since my delta x is 1, right, I know, and my dx is also 1, I know that my dx is here and my dy is here in green. So you can see your delta y is a little bit bigger than your dy because your original curve f of x is higher than your tangent line. Okay, so we've drawn our picture to show this, but I also know if my m is rise over run, I know that 2 is my rise or my dy over my dx, right? And I know my dx is 1, so 2 is dy over 1, or 2 is my dy. And that matches up with this equation we have here. F prime was 2, dx was 1, so my dy is 2. Okay. So this is my change in y on tangent line when x equals 1 and dx equals 1. Okay, and this is when x equals 1 and delta x equals 1. So basically what we're doing is given a specific point of tangency, if I change my x by a specific amount, I'm comparing what is the difference between the corresponding y value on the actual curve and the corresponding y value on the tangent line. Okay, so at the point of tangency, your x and y value will be the same on both your curve and your tangent line because the point is the same. But as I then move along the curve or move along the tangent line, if I look at the same x value and compare the y value on the tangent line versus the curve, we'll start to see some differences. Okay. And so they will get farther apart. And depending on what happens with the curve, like if with a quadratic, they're just going to keep getting farther and farther apart the farther I go along the x axis. But if it was a cubic that comes back down, what'll happen is they'll go farther apart and then closer together and then farther apart again. So depending on what your f of x looks like, the difference between dy and delta y will change depending on what that graph looks like. Okay. And that is all for today.